actually graphs, but they're harder to do on a computer. All right, so suppose we find a tangent line to a curve that looks like this. So let's say I've got this spiral here. All right, I want to find the tangent line, say right here. So what do I need to know? Well, I need to know if t changes a little bit, what is the slope of the line between here and here, right? So I'm going to get a line facing back that way, and I guess, for that matter, suppose we just get linear approximations to x and y as functions. Let's try this. So, example, suppose I get the tangent line to, well, let's just do the circle for now. So I've got cosine of t, sine of t, and let's look at t equals pi over 4, because we know what that's supposed to look like, right? So we got a circle at pi over 4, we're right here. So if this thing's going to work, we better get a line with slope -1, right? So let's see if we can do that. Let's see if I'm going to run out of markers. Heavy one. All right, that'll work. All right, so at t equals pi over 4, what is the linear approximation to cosine of t? Well, how do you find a tangent line approximation? You look at the first derivative, you evaluate it at the point, and you use point slope formula to find the equation for the line, right? So, all right, this says dx dt is negative sine of t, and dx dt evaluated at t equals pi over 4 should be negative root 2 over 2. Okay, so this is going to be, let's see, and what is the point of tangent, see? Well, x and t, so when t is pi over 4, cosine of pi over 4 is root 2 over 2, right? Okay, so point slope formula says this is x minus root 2 over 2 is equal to my slope, which is negative root 2 over 2, times my dependent variable, which is t minus pi over 4. Right? Okay. So this says x is equal to negative root 2 over 2 times t plus root 2 over 2 plus root 2 over 2 times pi over 4. Okay. Now I want to make sure this looks right. I may or may not be doing something ridiculous. Okay, so for the cosine of t, cosine of x. Okay, and then this one is supposed to be negative square root 2 over 2 times x plus square root 2 over 2 times 1 plus pi over 4. Okay, all right. Take a look at this. It actually does look like a tangent line right there, right? It's just an ugly one. Okay, so what we have is a linear approximation to a cosine right there. All right. Let's do the same thing for sine. So similarly, alright, a linear approximation to sine of x, or sine of t, let's see. Alright, so dy dt, if y is going to be sine of t, dy dt is going to be cosine of t, okay, and so at pi over 4, dy dt is going to be cosine of pi over 4, which is root 2 over 2, so I get a positive number, okay, so this should be y minus sine of pi over 4, which is this, is equal to the slope, root 2 over 2, times t minus pi over 4. Okay. So this says that y is equal to root 2 over 2 times t minus root 2 over 2 times what? 1 minus pi over 4. Okay, so let's see if that works. Knock these out. Sine of x and square root of 2 over 2 times t times x minus square root of 2 over 2 times 1 minus pi over 4. Doesn't look right. Oh, plus. Okay. So, again, we got a decent approximation to sine right there, right? And so the question is, if I've got approximations to sine and cosine separately, what if I use them both on the same graph, right? Because that says my y-coordinate is approximately this, and my x-coordinate is approximately this. So let me plot these two against one another on the same frame as sine and cosine plotted together, and let's see if what we get looks like a tangent to a circle. All right, so what I want here is cosine t, sine t. Okay, I want t to go from 0 to 2 pi. Okay, so if I make this guy my x-coordinate, and this guy my y-coordinate, see if it'll let me do it without changing all the t. Nope. Alright, so t and t. Okay. Check it out, it actually does look like a tangent line to the circle, right? So that's the key, is if you can get linear approximations to your x and y functions, you just put them together and it's a linear approximation of the curve. Now, if you look at this, these are horrible looking equations over here, but what do you notice? That's a linear equation, that's a linear equation, right? So, alright. Now, that's not how we normally look at a line, right? Because that's a parametric version of that line, right? Because it's going into a very specific place, and it's parameterized in terms of t. So, how could you get y as a function of x at that particular line? Well, we've got x and y as a function of t, So I can solve for t as a function of x, and then plug that in where the t is, right? So let's do that.
It's like Lagrange multiplier.
Let me think about that. Same idea. Yeah, like solving for lambda and yeah, right. Okay. So I'm gonna get some of these out of here. Put them in there. I just want to be able to see them. All right. Some of this chaos off the board. Okay. So what I've got is x is negative root 2 over 2t plus root 2 over 2 times 1 plus pi over 4. All right. That means x minus this business times 2 divided by negative root 2. That's what t is, right? Okay. Now I know that y is what? It is square root of 2 over 2 times t plus root 2 over 2 times 1 minus pi over 4. Okay. So square root of 2 over 2 times all that horribleness plus root 2 over 2 times 1 minus pi over 4. Okay. So what I've got here is 2 over root 2 with a negative out front times x minus root 2 over 2, 1 plus pi over 4. So I'm going to have a bunch of stuff canceling, right? The two things on the left hand side are just going to cancel. This is negative x minus, so it'll be negative x plus root 2 over 2 times 1 plus pi over 4 plus root 2 over 2 times 1 minus pi over 4. So more stuff's going to cancel. Which one cancels? Which one stays? Yeah, the pi over 4th term cancels, right? And so what I get is y equals negative x plus root 2 over 2 plus root 2 over 2, also known as negative x plus square root of 2. Alright, so quick check. Y equals square root of 2 minus x, same line. So, gotta be a quicker way to do that, right? So I wanted to see the principle of it so you can see where the linear parameterization is just a linear approximation to your curve. That's how you're getting your tangent line. So what's a quicker way? So think about how the slope came out. What's it?
Well, usually we use the derivatives and then we'll plug in that point of dx.
Right. And we did the same thing with the linearization, right?
Yeah.
So the two slopes I had in question were this guy, this was the x slope, and the y slope was this one, right? So what happened? When I solved for t, that one got flipped upside down, right? That's that 2 over negative root 2 on the outside. This one stayed the same. So you notice anytime I do this process, what am I going to do? I'm going to divide by this slope, and I'm going to multiply by this slope. That's going to happen every time I do this, right? So your shortcut, the slope of the tangent line, it should be dy dt divided by dx dt. Which again, this is getting to my point of whatever it is you're looking for, replace it with the appropriate function of t, and it's usually what you want. So, because we usually want dy dx, right? So in this case, everything's just a function of t. All right, so let's try that. Let's do the easy route for an ugly looking curve. we can do that. Suppose we want to find the tangent line to this guy. Oh, and then starting at 0, suppose I go back to negative 2 pi. Ooh, okay. So didn't expect that to happen. So, but your y coordinate's a square, so it's going to come back up. All right, so, oh, that's fun. All right, so suppose I want to find the tangent line when t is equal to pi. So what I've got is x is t cosine of t, y is t squared. I want to find an equation for the tangent line when t is equal to pi. Okay, anytime you want to find the equation of a line, what you need is a point and a slope, right? Now I know the slope's going to be the ratio of the two derivatives. Slope is dy dx, also known as y prime divided by x prime. Y prime is 2t, x prime is product rule, right? So negative t sine of t plus cosine of t. Okay, and so what am I looking at? Oh, when t is equal to pi, what do I get? I get 2 pi over negative pi sine of pi, which is 0, plus cosine of pi, which is negative 1. Okay, so it's negative 2 pi. That's what my slope is. All right. And what's the point that it passes through? Well, it would be x and y when I plug in pi, right? So it would be pi times cosine of pi. So x of pi is negative pi, and y at pi is going to be pi squared. Okay, so I have a point and a slope. So this tells me that y minus pi squared is going to be negative 2 pi, which is my slope, times x plus pi. Okay, so y minus pi squared equals negative 2 pi x minus 2 pi squared. So y is negative 2 pi x. What, minus pi squared, is that right? Let's add that on to both sides. Okay, let's give it a shot. Plot it on there and see if it looks like a tangent line to this thing. Okay, negative 2 pi x. Okay, plus, minus pi squared. So minus pi squared. Ooh. Okay, and that actually looks right? So it says when t is equal to pi, this is the place I'm at. Yep, that's about negative pi on the x-axis, and looks like about pi squared on the y-axis. So there's our tangent line. All right. Anything too terrible so far?
Why is it on the negative side? The slope on that side, not on the other.
Oh, it's just because that's where we happen to be when t is equal to pi.
Okay.
So, and that's the problem. It's hard to tell where you are on the curve. Let me put a slider in here. Let's see. If I do s times cosine of s squared. That's a point on the curve, right? Okay, so if I slide that over to t equals pi, or to s equals pi, you see where I'm getting right to that point? So, and if I'm at negative pi, I think that's probably the one on the other side. Yeah, so it's just because of the way the function is oscillating. So, all right. So as far as where we're headed with this, something else we're going to be dealing with, area below the curve. What do we normally do to get the area below the curve? Well, you would integrate y dx, right? What do you think that's going to turn into when you convert everything to functions of t? Well, y is a function of t. What are you gonna replace dx with? Yeah, dx dt. dt. So you got y times x prime. So you see what I mean? Anytime you have a d of something, you just replace it with a derivative, and then you have your t as your integration variable. When we do arc length, remember we had that symmetric formula that we said the change in arc length was like a hypotenuse of a tiny triangle? So we had a dx squared and a dy squared added up under a radical, and you can see what that's going to turn into. You're just going to square two derivatives, add them up, and put them under a radical. So we got that coming up next week. I think that's a decent place to cut off. Let's see. So we got tomorrow, next week. It's Monday. There is a Wednesday class, I think. I'm not expecting attendance to be stellar, but
You are holding it?
yeah, I'll be here.
Okay.
So
I have a question.
Mhm.
Will there be class on Wednesday?
yeah.
Can you pull up the screen? Can you pull it up?
Oh yeah, yeah.
Yay.